Hi, my name is Kevin Greer. I lead the Foam team at Google, and I'm going to give a quick explanation and demo of reactive programming in Foam. So, reactive programming, or maybe you've heard it called functional reactive programming, is a lot like the way normal spreadsheets work. So, in a spreadsheet, you're not explicitly coding observers, observables, callbacks, events, listeners. You're just declaring your relationships, and it's the responsibility of the system to maintain those relationships for you. So I've coded a little spreadsheet here in Foam. We can see some are just simple numbers, others are formulas. This one takes a sum of a range. And if any of those dependent values change, the value is updated automatically. So if I can say 3, then the cost is updated as of all the totals. So that's a much better way to program because you're not going to get a lot of the errors that you get from when you do events or performance issues. You may get multiple events for each dependent value and then maybe updating more than is necessary, or you may forget to unsubscribe from an observable and then continue to get events after you no longer care. But sort of the beauty of the spreadsheet is that you just declare what you want and it takes care of all of that for you. And it's ironic that this has been around since 1979 in what's technically the world's most popular programming language, the spreadsheet, and yet we haven't seen this functionality move into, say, the second most popular programming language, which is JavaScript, or the second, third, or fourth most popular programming languages either. And so the main feature of Foam, the feature-oriented active modeler, is modeling, but we have added reactive programming, and we're quite pleased with the results. Okay, but let's look at how we extend that in Foam. So in Foam, you can say this dot dynamic and then give it a function. And then any of those dependencies in that function are automatically maintained for you. So I can say that the clock's x and y equal the mouse's x and y. Now, as I move the mouse around, the clock automatically moves. No events, no listeners. It's just purely declarative. But if I add another clock and I say that it's a function, its x and y are functions of clock two's x and y, and clock one's x and y are functions of the mouse, as in the previous example, then I get both clocks moving. And this is just like in the spreadsheet. You can have whole networks of dependencies, and they're all maintained. Okay. There's something else interesting we can do. Say we wanted to model time. We can say we're starting off at time 0 and say I buy 2 of these a month, if my units are a month. And then as time goes on, the number of these that I buy and my total goes up. Well, let's say that the time, so basically we're saying time equals time plus 1. Okay, so now I've animated the time, and all the dependent values are animated as well. Now, I'm just animating numbers, so that's not very interesting, but we can take that same concept and apply it to arbitrary objects, including graphical ones in Foam, and then we get like conventional animation. So back to the clock demo. If instead I take the second clock's position to be a function of the first clock's position, plus some trig applied to timer.time. So here you can see this is with modeled time into a little time object. And I'm making the position be a function of the timer's time, which is this value right here. You can see I can interact with the time. I can stop it, step, start it back up. Then we get animation. But what's interesting is that we didn't have to explicitly create an animation system. This just falls naturally out of our reactive programming if we happen to react to time. Now we can look at a more kind of complete example of that. So here I've got a little solar system, some planets orbiting the sun, some moons orbiting the planets. This graph is plotting the position of one of the planets. These eyes, you can see they're always watching Mars here. We've got the clock and it's all going. So this is basically just a spreadsheet, but broken out of the confines of the two-dimensional grid and generalized to work with any object. Now we can see here we have this time wheel, and this is also bound to time. But it's not a function of time, it's a relation. Or as you would say in the JavaScript world, it's not a one-way data binding, it's a two-way data binding. So if I grab it, I can stop time. Now I can scratch time like a DJ and make time go back and forth. You can see the planets go back and forth. Okay, so it's not a slave of time, it's just appear in time. There's nothing special about time. I can bind time to a view, I can control time. There's nothing special about it. Now I can declare those formulas to be anything I want. But if I happen to make those formulas be from physics, say things like gravity, friction, inertia, then I get physics without the physics engine. So what I've done in this demo is I've added negative gravity to the small blue circles to make them buoyant. And I've set the friction to be quite high to kind of simulate moving through water. And then we have collision detection, which is doing the bouncing, and then we let it go. So here we can see collisions, and the different objects have different masses. We have springs, collision and springs. I'm not really sure what this one's demoing, but it's fun. So again, we didn't write a physics engine. It just kind of fell naturally out of reactive programming. So if you remember, I said the main design feature of foam is that it's a modeling system. So our code is modeled. So our code is data just like anything else. So if I look at this animation, it's the angle that he bends his wing or tail. Those are functions of time, and that's what makes it be animated. So it's obviously it's a function of time, but it's also a function of its own code. So here's the paint method. Here's the tail. So if I comment that out, so with only one slash, I have a syntax error. On the second slash, I have valid code again, and the tail is gone. Okay, so what I'm doing now is live coding. Okay, so now we go up to the wing function. I'm going to make that rotate quite a bit more. Let's make the wings longer. It's too long. Up here we've modeled time. Let's slow that. We have a time warp function, so let's slow that down. Okay, so that's something pretty interesting. I can grab the time wheel. So you notice that I haven't thrown out the program and reloaded it on each keystroke. I'm editing the object while it's still running. So if I change some parameters on the wing, it's right in the same position. I'm kind of acting on the object while it's running. Okay, so that's it. That's reactive programming in foam. The interesting thing is that it's built in right in every object. So we can animate graphics, we can animate physics, we can animate your salary. It doesn't matter. It works on everything. And because we did this one powerful concept really at the low level, we're picking up things like animation, physics, and live coding almost for free. And so that's one of the things that contributes to foam being so small despite its many features. So that's it. Thanks for listening or watching, I should say.